Section: Introduction. In this section, we discuss the concept of in-context learning, which is a key feature of large language models, LLMs. In-context learning allows us to use a pre-trained LLM to solve problems by providing the problem description and relevant data directly within the LLM prompt, without needing to update the LLM parameters. This capability emerges from the training data of the LLM at scale, rather than being explicitly taught. Researchers have been exploring in-context learning since its discovery in the GPT-3 model. Studies have looked into the mechanisms behind in-context learning, conducted practical experiments, and applied in-context learning in various tasks. While most of the research has focused on prediction or supervised learning tasks, there is growing interest in using in-context reinforcement learning, ICRL, for decision-making processes. Decision-making agents, like LLMs, need to have three core capabilities: generalization, exploration, and planning. In this paper, we concentrate on exploration, which involves gathering information to evaluate options and reduce uncertainty. Recent studies have shown that transformer models can exhibit exploration behavior in reinforcement learning tasks when explicitly trained for it using data from reinforcement learning agents or expert demonstrations. To investigate whether contemporary LLMs can explore in context, we conducted experiments using LLMs in simple reinforcement learning problems called multi-armed bandits, MABs. MABs are a fundamental type of RL problem that focuses on the balance between exploration, trying different options, and exploitation, choosing the best known option. By studying how LLMs perform in MAB environments, we found that only specific prompt designs led to successful exploration behavior, while others failed to converge to the best decision. Our experiments showed that with the right prompt design, state-of-the-art LLMs can effectively explore in simple RL environments. However, more complex environments may require additional algorithmic interventions to enable LLMs to explore effectively. This suggests that while current LLMs show promise in simple settings, further training may be needed to enhance their exploration capabilities for more challenging tasks. Section Summary. In this section, we explore the concept of in-context learning in large language models, LLMs, where the models can be used to solve problems by specifying the problem description and relevant data within the LLM prompt without updating the model parameters. We investigate whether contemporary LLMs exhibit the capability to explore in context by deploying them in simple synthetic reinforcement learning problems, specifically multi-armed bandits, and find that while state-of-the-art LLMs can explore in simple environments with carefully designed prompts, they may struggle in more complex settings without external summarization of the interaction history. Section: Experimental Setup. In this section, we examine the experimental setup for the multi-armed bandit, MAB, problem. We are dealing with a specific type of MAB called stochastic Bernoulli bandits, where there are k different actions, arms, with unknown mean rewards. The goal is to maximize the total reward by selecting the arm with the highest mean reward. In this setup, the rewards for unchosen arms are not revealed, requiring exploration to find the best arm. We focus on MAB instances where the best arm has a mean reward of 0.5 plus, delta 2, while all other arms have a mean reward of 0.5, delta 2, with delta being the gap between the best and second best arm. Our main instance has k equals 5 arms and a gap of delta equals 0.2, which we call the hard instance. We also have an easy instance with k equals 4 arms and delta equals 0.5. To interact with MAB instances, we use language model models, LLMs, as decision-making agents by providing them with prompts describing the MAB problem and the interaction history. The prompts can vary in scenario, framing, history presentation, requested answer format, and the option for a chain of thought explanation. These choices lead to 32 prompt designs, each potentially aiding the LLM in decision-making. We experiment with 3 LLMs, GPT 3.5, GPT 4, and Llama 2, considering different prompt variations and temperature settings. A temperature of 0 makes the LLM deterministic, while a temperature of 1 introduces randomness. We identify each LLM configuration with a 5-letter code representing the prompt design and temperature setting. Most experiments focus on the buttons scenario, with the advertisements scenario used as a check. Section Summary. In this section, we set up the experimental environment for studying multi-armed bandits, MAB, focusing on stochastic Bernoulli bandits with k possible actions and mean rewards associated with each arm. Our goal is to maximize total reward by identifying the arm with the highest mean reward, emphasizing the need for exploration due to unrevealed rewards for unchosen arms. We explore different prompt designs for language model agents, LLMs, interacting with MAB instances, considering scenarios, framing, history presentation, final answer format, and the use of chain of thought explanations to enhance decision-making capabilities. Section Paper. In this section, we will discuss the baselines we used for our experiments. We looked at 2 common multi-armed bandit, MAB, algorithms, UCB and Thompson sampling, TS, which are considered good in theory and practice. We also included the greedy algorithm, known to not explore well. Although these algorithms have adjustable settings, we did not tweak them. Additionally, we tested the epsilon greedy algorithm with different epsilon values to show the balance between exploring and exploiting. We ran 1,000 trials for each baseline and MAB setup. Our main experiments had a time limit of t = 100. To consider randomness in rewards, we ran n = 10 or 20 trials for each setup. As a check, we also ran a single experiment with GPT-4 for 500 rounds, n = 20, and got consistent results. For GPT 3.5, we used n = 20 trials for 48 different setups, totaling around 200,000 queries. GPT-4 was more expensive and slower, so we only used n = 10 trials for 10 setups, resulting in about 50,000 queries. LLaMA2 was cost-free but performed poorly, so we limited our tests to 32 setups with n = 10 trials. Bandit experiments with language models, LLMs, are expensive and time-consuming. They require a large number of queries to the LLM for each setup to get reliable results. Both n and t need to be large, especially for challenging MAB setups, to overcome randomness and allow algorithms enough time to find the best choice. We found that most LLM setups failed to explore effectively, except for one GPT-4 setup. These failures were due to either not selecting the best choice early on or not eliminating poor choices. Our results are summarized in scatter plots and tables, showing the differences between LLM setups and traditional algorithms like UCB and TS. The successful GPT-4 setup explored well and performed better as a result. Section Summary. In this section, we considered standard multi-armed bandit, MAB, algorithms like UCB and Thompson sampling, along with the greedy algorithm, which lacks exploration and tends to fail. Our experiments involved various MAB instances with different configurations, including epsilon greedy, to showcase the trade-offs between exploration and exploitation. Despite the high cost and time involved in running experiments with language models, LLMs, for MAB problems, we found that most LLM configurations exhibited exploration failures, except for GPT-4 with a specific configuration, which successfully explored and converged to the best arm. Section: Identifying failures. In this section, we provide a detailed overview of the exploration failures shown in the scatter plot and table for GPT-4. We also present additional results and figures that highlight these failures in more detail. We focus on GPT-4 because we observed that GPT 3.5 and Llama 2 perform worse in all our experiments. We start by explaining the surrogate statistics, SUF fail freak and min frac, which help us measure failures in exploration. SUF fail freak helps us identify suffix failures, where the best arm is not chosen even once after a certain number of initial rounds. This indicates a long-term failure to explore, similar to the behavior of the greedy strategy. We use suff-fail-freq to quantify how often these suffix failures occur in our experiments. Most of the LLM configurations we studied show bimodal behavior, where some replicates rarely choose the best arm, while others quickly converge to it. This behavior leads to a high incidence of suffix failures. These failures cannot be fixed by running the algorithm for longer because without exploring the best arm, we cannot learn if it is indeed the best. We also discuss uniform-like failures, where the LLM selects arms almost equally throughout the rounds, failing to focus on the better arms. We use min-frac to measure these failures, where a higher min-frac indicates a more uniform selection of arms over time. Our analysis shows that most LLM configurations, except for one, exhibit either suffix failures or uniform failures in challenging scenarios. We summarize the performance of each configuration using statistics like suff-fail-freq, min-frac, median reward, and greedy frac. Overall, we found that GPT-4 performs better than GPT 3.5, while Llama 2 performs worse, especially in terms of suffix failure frequency. Additionally, we observed that small changes in the prompt design can significantly impact the performance of LLMs, but understanding how different modifications interact with each other remains a challenge. Section Summary. In this section, we provide a detailed overview of exploration failures in GPT models, focusing on GPT-4 and comparing it to GPT 3.5 and LLaMA2. We introduce the concept of suffix failures, where the best arm is not selected even after initial rounds, and uniform-like failures, where arms are chosen uniformly without exploiting better options. These failures significantly impact long-term performance and are crucial in understanding the behavior of different language model configurations. Section: Investigating Successes. In this section, we explore the successes and root causes of our experiments with LLM-based decision-making agents. We found that on the challenging MAB instance, only the GPT-4 with the BSS-wide text C0 prompt design managed to avoid certain failures and performed well. When we ran GPT-4 BSS-wide text C0 on the hard MAB instance with t equals 200 and n equals 40, we obtained more meaningful results. We also looked at GPT-4 BSR-wide text C0 as a comparison, which showed different behavior. Our experiments indicated that BSS-wide text C0 continued to perform well without certain failures, especially for larger t, while BSR-wide text C0 exhibited a significant fraction of failures. Visualizations further supported the success of BSS-wide text C0 over other configurations. Our experiments shed light on how LLM-based agents behave, but it's important to understand why they behave the way they do. We considered two hypotheses. Either the configurations are too greedy or too uniform-like. By analyzing the behavior of GPT-4 on easy and hard instances, we observed differences in performance. On the easy instance, most GPT-4 configurations behaved similarly to a greedy strategy and performed well. However, on the hard instance, their behavior was more complex, neither entirely greedy nor random. Further experiments focusing on per-round decisions of LLM agents provided insights into their behavior under different conditions. These findings suggest that assessing whether LLM agents are too greedy or too uniform-like based on per-round decisions is challenging. Despite differences from baseline algorithms in longitudinal experiments, the behavior of LLM agents varied depending on the specific data source. This complexity highlights the need for further investigation into the decision-making processes of LLM-based agents. Section Summary. In this section, we investigate the success of GPT-4 with the BSS-wide text C0 prompt design on a challenging multi-armed bandit MAB instance. Our experiments show that this configuration avoids suffix failures, performs well in terms of reward, and behaves similarly to Thompson sampling (TS). Additionally, visualizations and statistics support the claim that GPT-4 BSS-wide text C0 0 is successful in converging to the optimal arm over time. Section: Related work. In this section, we discuss a recent body of work that focuses on understanding the capabilities of large language models, LLMs. These capabilities include general intelligence, causal and mathematical reasoning, planning, and compositionality. Our work specifically contributes to the broader literature on in-context learning capabilities. Previous studies have mainly looked at in-context supervised learning, with less attention given to in-context reinforcement learning. Some empirical studies on in-context reinforcement learning have focused on models trained from scratch using trajectory data from another agent. These studies show that pre-trained transformers can implement exploration strategies like Thompson sampling and upper confidence bounds. However, these works require modifications to the pre-training phase of the language model and do not investigate if existing LLMs have exploration capabilities under standard training conditions. There is also a growing body of work applying LLMs to real-world decision-making tasks, such as gaming, programming, and medicine. Some researchers have introduced generative agents simulating human behavior and LLM-enabled robots. Additionally, there are studies evaluating LLM performance in tasks like two-armed bandits to characterize intelligent agents. Moving on to multi-armed bandits, we provide background information on the problem and the baseline algorithms used in our study. The upper confidence bound, UCB, algorithm explores by assigning each arm an index based on the average reward and a bonus term. We use a version of UCB with a specific setting for the bonus term. Thompson sampling, on the other hand, assumes the arm's mean rewards follow a Bayesian prior and chooses arms based on sampled mean rewards. Both UCB and Thompson sampling have proven regret bounds, which measure the algorithm's performance compared to the best arm. These algorithms achieve nearly optimal regret rates in our experiments. In contrast, the epsilon-greedy algorithm is inefficient as it does not adaptively explore better performing arms, leading to higher regret rates. The greedy algorithm, which does not explore at all, can result in failures when initialized with limited information about each arm. Section Summary. In this section, we explore the capabilities of large language models, LLMs, in in-context reinforcement learning, a less studied area compared to in-context supervised learning. Our work focuses on investigating whether pre-trained LLMs possess exploration abilities without intervention during the pre-training phase, unlike existing studies that require such interventions. We compare our findings with other studies on multi-armed bandits, showing that while simpler instances may showcase good performance of LLMs like GPT-4, they may not provide substantial evidence of principled exploratory behavior. Section: Discussion and Open Questions. In this section, we discuss our findings and raise some questions. We found that current LLMs may not explore enough for basic statistical learning and decision-making tasks without additional help. We suggest some steps to test this idea further and find ways to improve the situation. Given our results, we can try a few interventions. One option is to change the prompts we use to see if that helps. We could also try giving the LLM examples of exploratory behavior in the prompts or train it to use tools like a calculator or a randomizer. However, these steps can be challenging due to costs, model access, and computing requirements, especially when we need to run many experiments over long periods to get reliable results. Therefore, we think it's crucial to develop better methods in statistics to study and understand LLM behavior more efficiently. By focusing on simple problems like multi-armed bandits, we can carefully study how LLMs explore and test different interventions. Failures in exploration in these basic tasks may indicate similar issues in more complex decision-making scenarios. However, we need to be cautious when applying solutions from simple setups to more complicated problems. For instance, what works for a multi-armed bandit setup may not work for more complex situations like contextual bandits with high-dimensional data. We need to explore different interventions to see how well LLMs can function as decision-making agents.